Let's move on to this next topic about observability. Observability is conceptually, it's saying the story of whether we can, based on our observations, these are our observations, the outputs are our observations. We don't directly see the state, but instead we see the output directly. Observability conceptually means that can I infer my state from my output, from what I observe? And more specifically, it's saying that can I, more specifically, for the linear system like this, it's actually saying, can I infer the initial state from whatever I can measure? I can measure, if I can measure just 1, or if I can measure 2, if I can take 2 measurements, can I infer the state directly? This is not always true. For example, if you have a 3x3 matrix system, C, let's say, is 1, 0, 0, and then x0 is 3 by 1. What you are going to have is y0 equals to 1, 0, 0, and then x1, 0, x2, 0, x3, 0. So the first measurement you get is only x1, 0. You don't see the direct order states, x1, x2, and x3. And if you can keep on doing this, you get y1 is x11, x21, x31, which equals, so x1 equals c, for this, let's start with the simple case. x1 equals to a times x0. So is c times a times x0. So you can see, over here, you don't directly get all the initial state either. It's going to be some linear combinations of all these states over here, depending on your structure of A. So using 2 measurements, y0 and y1, there's no way you can tell all the initial states, x1, 0, x2, 3. There are 3 variables over here. You only have 1 equation, 1 linear equation, and another linear equation. So 2 linear equations, but you have 3 unknowns. You can't solve for the initial state. So the controllability, the observability condition, therefore, is important to analyze very carefully. To be rigorous, now you can see that the condition should be, can I infer x0 from the outputs in finite amount of time? Using just a finite amount of outputs, can I infer the initial state? And you can see, if I can infer x0, that means I can tell everything about the states, because x1 becomes null. So x1 will be null, and continue x2 will be null, and so on. So we only need to be able to solve for x0, and then all the rest of the states will come from the state equation, the system dynamics. Now, mathematically, what does that mean? Let's start with this simpler case. Mathematically, that means we can write things a little bit more nicely. Using the same kind of logic, I'm just going to write things in a more compact form. So y0 is c times x0, and y1, we saw, is c times x1, which is ca times x0. You can keep on doing this. y2 is ca squared, and then continues. So this seems to be a matrix vector equation. Matrix multiplied with a vector, this is a vector, and we're interested in when can we solve for this vector. So it's again a linear algebra question. So we know that the solution actually depends very heavily on the structure of this matrix. That's the first observation. The second observation is, you can see the pattern over here. You got C, you can actually write it as C times identity. C times identity, C times A squared, C times A to the power of 3. So in the end, you're going to have something like C, I'm going to stop at CAN minus 1, and then you have here YN. This structure over here, you can see we have something that's actually very much related to the controllability case. I have these patterns of A matrix appearing, and it's just that in this case, we are not adding columns to the controllability matrix. We are adding rows to this matrix, this QD matrix. When I have one more measurement, I'm going to stack more rows to here. So what do we know about the Cayley-Hamilton theory? Similar to the controllability case, it's saying actually you don't have to use really significant amount of outputs if you are interested in solving this equation. Because you add more here, the next one will be CAN, and then AN is a linear combination of the previous components in this matrix. So what's going to happen is you can keep adding more, but it won't help to solve the linear equation. So you can just stop at CAN minus 1, in other words. We have a few observations now. So the solution depends on QD's properties, and we don't have to go to take a lot of more measurements if the system dimension is n. And then when we pick the matrix to stop at CAN minus 1, this is called the observability matrix. Now let's dive a little bit deeper. The matrix QD, let's say let's check the dimensions, similar to how we check dimensions of the controllability matrix. If it's single output, what is the dimension of this matrix? If it's single output, means that C is a row, a single row, just like what we did in the example. And then what we're going to have is QD is C100 times CA, and then CA squared, right? N is 3, so I stop at CA squared. Here, the dimension of this one, don't be confused about the symbolic representations. If C is a single row, C times A is going to be also a row vector. C times A squared, or C times A to the power of 100, 200, is still going to be just one row. So therefore, this is 3 by 3. If the single output, then QD is a square matrix. And then if it's not, yes, question?
Is C always a row matrix?
No.
Okay.
So that's the next point. If you have multiple output, let's say you have NO, the number of outputs, then the dimension of Q is going to be, this is going to be multiple rows over here, and another multiple rows over here stacked together. There are n of those elements, right? So in this case, you have 3 of these elements, 3 rows. If you have NO, then it's going to become n times NO rows times n columns, which is going to be a tall matrix or a wide matrix. So you have n columns, and then you have n times NO rows, well, NO is larger than 1. So it's going to become a tall matrix. QD is going to become tall. Now, regardless of whether these two cases, whether it's a square matrix or a tall matrix, what is the condition for this matrix vector equation to have a solution? So now let's talk about the solution concept. To be able to have a solution for this equation, we need, first of all, the vector on the left-hand side, this must be in the range space of this QD, right? What you have is a bunch of columns over here, and here x0 is simply, this is a linear combination of the columns of this matrix over here. So for it to have a solution, first of all, this Y matrix, this Y vector, let's call this capital Y. It must be in the range space or linear combination of QD's columns, which is actually which is true by definition. So y0 equals ci times equals c times x0, y1 equals ca times x0. This is already by system definition. So obviously this is indeed expressed as the right-hand side is a linear combination of the columns. So this one is very easy. And then the second one is, now it's easier to visualize if it's single input. If it's SISO, if it's single input, if QD is square, if QD is square, then we are having a square matrix QD times a vector x0 equal to y. If this matrix is invertible, then, or in other words, QD is non-singular, then you have this solution. In other words, we need this QD to have rank n. All right? To be invertible or non-singular. This is if you have single input, we achieve at this rank n condition. If QD is tall, you are going to have this structure. So that means you collect a lot of outputs. You collect more outputs, and the vector y is longer, is taller than x0. So what is the condition for this equation to have a solution? So in linear algebra, you learned this. This is actually the fundamentals of linear algebra. If, for example, you have 1, 0, 0, 1, and then 1, 1. This is a tall matrix. Let's say this is a special case over here. And then you need to solve x1, 0, x2, 0. And then outputs, you have 3 outputs. How do you solve this equation? You use something called Gauss elimination, right? You try to remove make the last row to be all zeros. That's the Gauss elimination to solve this equation. For the square part, there is a square portion over here. The square portion, you require that all the remaining rows to be able to be expressed as linear combinations of the previous rows. And then the solution will always exist if the rank of this matrix is 2. It has full column rank. So that's the condition for the observability to hold. And you can see, actually, for the special case, you have rank n is also rank n. And then it's full, be very careful, it's full column rank. In the controllability case, it's full row rank. And in here, it's full column rank. Because QD can be potentially tall matrix, it's impossible for it to be full row rank. if it's multiple input actually. You have this many rows, and it's impossible for all of them to be linearly independent if the column is, you only have n columns. And then similar to the controllability analysis, this matrix being full column rank also corresponds to a Gramian property. This being a tall matrix means that sometimes it's not as easy to do numerical computations. Square matrix is always nicer. It has determinants. This one doesn't even have determinant. So square matrix can have advantages in practice. We have a equivalent observability condition, which is the Gramian, the observability Gramian. I'm going to use W, O observability Gramian, D in the discrete time case, which is QD, this tall matrix, potentially tall matrix, QD transpose times QD. This is the concept. So it is QD transpose. You're going to have QD is CA n minus 1. So QD transpose is going to be C transpose, A transpose, C transpose, etc. So the product is going to be summation. You have C transpose times C, and then in the middle, in the second term, is A transpose C transpose C. So you always have a C transpose C in the middle. And then on the left, you're going to have A to the power of, I'm going to use K as the index. Okay, so it's going to be A transpose to the power of K, and then K indexes from 0 to some finite number. Let's call it K1. So this is the concept over here. The main result is that you're going to have now a wide matrix multiplied with a tall matrix. This becomes n by n. It's a square matrix, so you can compute the determinant. You can check whether it has full rank very, very easily. This one, similar to the controllability case, when you take K1 to be infinity, if A is stable, if the system is stable, taking K1 to infinity will lead you to something similar to this. So this is actually the solution to a Lyapunov equation as well. The structure of the Lyapunov equation is Q is C transpose C, and then you can, this one is actually easier than the controllability case. You can see the structure of A actually is exactly the same in this equation and this equation. So on the right is AK, on the left is A transpose K. So therefore, this one is the solution. If A is stable means the eigenvalues are inside the unit circle. Then this is W A transpose WOD A minus WOD equals negative C transpose C. So the observability Gramian, when the system is stable, can be solved from this Lyapunov equation. A transpose WODA minus WOD is negative C transpose C. So you don't have to numerically just try some number K1 until you find this product becomes non-singular. You can solve this and immediately have an answer. So that is the observability Gramian. We have the condition on the screen. These two are the same. If the Gramian is non-singular or is invertible for some finite K1, then the system is observable. And for the case, if A is square, if the system is stable, K can be set to infinity, and the Gramian can be solved by solving this Lyapunov equation. We talked about the controllability canonical form, and then system in that form is always controllable. Let's look at now the actual reason for the term of observable canonical form. This is the observable canonical form. C is 1, 0, 0. A has the first column to be filled with the coefficients A0, A1, A2. By this one, if we construct the observability matrix, we have C is the first row, so it's 1, 0, 0. And CA is actually C times A is going to be the first row of A, so it's negative A2 and 1 and 0. And then CA square, you compute, it gives you this. So the observability matrix, you can see now, is non-singular because of the structure. It's 1, 1, 1 in the diagonal and then 0, 0, 0 on the top right. The observability matrix here is full rank, and the system in this observable canonical form is observable. So that's the reason why this canonical form is called OCF.